get started, I just want to preface this by saying I have a horrible cold, and Mr. Ziccarelli was nice enough to say he would speak for me, so if you would come on up here.
Sure, but could you say that again? I can't hear you.
Hi, we are Team Vibranium. I'm Harold Hastings. This is Alexander Zuleta, and we're going to be going over a shape memory alloy passive shock absorber. Now, a more appropriate name would have been a hysteretic or hysteresis powered shock absorber or damper, from what we found later in our research. Next slide. The purpose was to design ultimately a prototype, a proof of concept that this could actually be done, because in our initial research we didn't have the knowledge of the language of what we need to be looking for, because we were looking for terms like shock absorbing, damping, and really what we need to be looking for was hysteresis and small films and small wires, and that was oversight on our part. The next part was to implement a thermal delivery system to control the phase transformation. We were successful in this ultimately. However, it would have been nice if we could have a feedback loop, so that way we could actually fix the temperature at a certain at a desired level. And last but not least was to actually change the damping ratio by altering the physical state of the material, changing from martensite to austenite. Next slide. This is our timeline. It has changed about 13 different times, so it's not going to match this as exactly as you see it, because we had to change our scope. We had some issues, a lot of manufacturing issues came up, but we'll talk about that when the time comes. This is our approach. We started with the design for our CAD. We also had an oversight on that. We actually designed our first prototype without having any way to mount it, so we couldn't test it. So after the third prototype design, we were able to get the correct one. Applied dynamic simulation to compare with theoretical values. We were able to use Autodesk Inventor SolidWorks. We had initially, we're trying to use ANSYS and Abacus, because those have the appropriate models for dynamic materials such as nitinol. That being said, Abacus, we could not really acquire a license to use, and ANSYS, they would allow us to use a license for a small amount of time, about a month, on the FIU's license. However, due to time constraints with work, family on both of our parts, and school, we weren't able to work that in. So unfortunately, we don't have very good dynamic analysis of this. Also, we need to characterize the material. We use differential scanning calorimetry to do that, and to test, control, and measure the system response, which Alexander will go over later. Next slide. This is our material selection. The primary purpose of this was to show that nitinol could indeed be used as a spring, and it has been shown empirically that it is a damper, depending on the state it's in. Next slide. These are some cursory calculations. We were operating on the premise that as long as our strain was within the 0.6 to 0.8%, we could assume that it had an infinite life. And so that's how we stayed away from the necessary fatigue calculations, which were very hairy and very nasty, considering that this is a dynamic material and we were actually carrying it through the phase change. Some more, this is basically all Springmaker equations. As you can see, we did calculations for both austenite and martensite. The way we calculate the Young's modulus was we actually measured the displacement of a spring with the given force, and we worked backwards to find the actual Young's modulus, not the book value. So this actually differs from about 40,000 for the 40,000 megapascals for the austenite and 20,000 megapascals for the martensite. That's why you see that deficiency. Next slide.
The next step, after we have the springs done, we need to, I'm going to rephrase this. Before we make the springs, we need to know what is the size of the material. We need to use a wire form, so we need to coil the springs. In order to know how much energy or current, in these terms we need to use, we need to calculate the resistance on how many amperage is going to pass through if we connect that to a power supply. So we iterated and we found that a viable, a very good diameter will be 1.9 millimeters. finding the resistivity of the material, the length of the stretch spring, and the voltage, we could find all these parameters like the current and power. Using 1.9 millimeters, we estimated around 400 watts. This graph describes how the current increases as we increase the wire diameter of the spring. Since we are connecting that to a power supply, we need to know all this data so we don't overheat it. And if we overheat it, we can damage the heat treatment, which is something that we're going to focus on later. What we need to design is the springs, which are going to be molded. They were made using these fixtures. The fixtures, what they do is they fix the material, we crimp it on the ends, and then we put it on the oven at 560 Celsius. 560 Celsius was determined based on a study, on the DSC analysis. The thermal delivery system is a microcontrol device which is using the Arduino Uno and a MOSFET PWM, pulse width modulation. So what we want to do is we want to control the heating quantitatively. So the next thing is the enclosure. So we want to enclose all the components and have them nice arranged. So we created a cylindrical configuration very similar to standard dampers. As you see, this middle white plate moves up and down, and also the springs move along with the plate. The green parts compress, just as a regular damper, just like that. So the manufacturing was making the springs. Next, the fixture. The fixture was made using wood, and we got the perforated wood so we could pass the little stick so we could make a truss. We used the oven to heat treat the material, and this shows how we did it. We crimped the wire to the ends, and then we processed with the heat treatment. The material characterization is going to give us what is the transformation temperature of the material. Nitinol is very special. It has a solid state phase transformation. So this temperature is determined by the process and by the mixture of components. In this case, nitinol and nickel. In the shape memory alloy, we can find 51% nickel, 49% titanium. That ratio will determine that. But in order to know, we need to run this through differential scanning calorimetry. What we do is we put a little piece of nitinol, which has been pre-treated, with the 3 iterations. We treated the nitinol at 460 Celsius, 510 Celsius, and 560 Celsius. These are the different temperatures that we annealed the material to. After we annealed that, we took the samples and we used the DSC machine and we got the graphs. These graphs will tell us when the transformation occurs. In the x-axis, we have the temperature. So we are speaking about 60 Celsius, 65 Celsius. Knowing this, we proceed with the heat delivery system. So we use the Arduino to create a control, and this will control the MOSFET PWM controller. This is high power. We separated the power sources. So this is a small battery. This source is this one that you see here. It provides high amperage because we need about 30 amps. So the MOSFET is limited because we also limited the current, so we don't have all the current going through and don't spoil the material. We have a power transistor too, and a meter. This ammeter, we needed to figure out a way to measure high current, since Usually those instruments are expensive. We build one with a shunt resistor. A shunt resistor is a small resistor, bulky. It can pass a lot of current, and it has a voltage drop. By measuring the voltage drop and the resistance, we can know how much current it passes through. And then the MOSFET connects to the springs. As you see here, we have two springs connected on the top and two springs connected at the bottom. So it's going to be two control springs on top, two control springs on the bottom. We are dealing with two types of alloys. We're dealing with supraelastic alloys and shape memory alloys. So what we say is we made a hybrid system that uses a supraelastic type and at the same time a shape memory alloy. The shape memory alloy was selected because it provides damping properties, while the supraelastic provides a spring behavior, but with supraelasticity, so it doesn't deform.
All right, so on to the experimentation. Some test equipment we used because we could not actually do any really valid computer analysis. We did actual experimentation using a 3-axis accelerometer, a voltmeter, excuse me, amp meter, thermocouple, oscilloscope, and a high amperage source, as you see here in front of you. This is some of the analysis that we were able to capture using the 3-axis accelerometer, based on our system dynamics calculations here, which a lot of this should be familiar to some of you guys. The damping ratio for the Martin-Siddick state was 0.3, and the austenitic state was 0.23. Now, based on some of the friction and other variables that we can't account for, we believe there's some drop in it that's really nominal, but it's not accounted for here. And as far as dynamic simulation is concerned, we did perform one, but once again, because nitinol is a dynamic material, we couldn't perform one at martensite and austenite, so we treated everything in austenitic state, and we performed a simulation in order to take that into account.
So using the previous simulation, we gave a weight, we gave an input, and then using time-based analysis, we capture a moment and we export that moment to FEA. So what we did is, directly from the software, it exported the forces, and then we selected the material, and then we computed the FEA. This shows the slider, which is the inner part that slides up and down.
Should you know that we optimized this assembly for quick assembly and disassembly just for this matter, so we can do demonstrations and to see what's happening with the system.
So this simulation is for the middle plate. So we perform the convergence rates to show that the analysis is good. We use adaptive mesh refinement, which it changes the mesh size in order to converge to a solution. This is the top lid. We found the bond miss stresses. Next slide. As you see here, these are the forces that occur in that dynamic simulation. There are moments, there are forces up and down in different directions. This displacement is a little bit exaggerated in order to see, but it's not a big deal. Didn't have too much. This is the top lid. It's this one. Next one. The convergence rate for top lid too, which shows it converges.
We're going to kind of fast track through here because it's more the
No,
same.
no, take your time. I mean, you can compensate on the question side.
Okay.
Yeah.
The bottom lid is the same, basically the same figures as the top.
In this simulation, when you see the arrows, it means that those are the forces caused by the springs. So these are no forces. That's how this simulation saw the forces. The bottom lid, you see the ball misses distributed up the middle. This is line test.
Okay. So as far as outcomes, we had two outcomes: expected, unexpected, expected, successful, patented, become millionaires. Effectively damp vibrations and reduce the transmissibility of those vibrations to the rest of the system. Unexpected, failure to determine fatigue, temperature transformation setting, and failure in the dynamic response. Out of these two, we weren't able to empirically or actually determine this with the funds and with the scope of the project that we had. As far as global learning is concerned, nitinol is a binary alloy. It's not the last one, it should be alloy. Titanium can be expensive because it is difficult to process. It is an abundant resource, though. I think it comprises about 9% of all elemental stuff on the Earth, and it's widely used in the medical field for biocompatibility, and the fact that it's so versatile makes it highly desirable. We explored local sourcing, and we also explored overseas sourcing. As far as the nitinol is concerned, we actually went with local sourcing because it was faster and we had better control of the material. Unfortunately, for overseas, it was cheaper, but it took a long time. We didn't have as much control. As far as local and foreign laws are concerned, and environmental impact, nickel release into the environment was a concern because with more nitinol, the more nickel needs to be produced, and a lot of chemicals that are required for the refining process are not so good and produce very bad byproducts. We have done a little bit of research into other fields, such as using it for earthquake damping system, for isolation tables, and some other things. We haven't really gotten into the scope for this. Environmental issues, I believe I went over that quickly, and alternative applications. As far as the cost is concerned, this figure is an estimate for man hours. That's why it's so high, around 7,000. Our actual cost to date is about $1,758 for everything that you see in front of you. This is the hands-on portion, our actual production. I don't know that guy.
All the rods were manufactured in the machine shop. We got the supplies, we cut to size, we rim, and also the fixture was cut with a Dremel. So there was a lot of hands-on work on this project.
While you're doing the questions, while you have your questions, we're going to set up a quick demo. All we should have to do is just turn the computer on, and you'll see the phase transformation take place, and it should lift the weights up. So take
It's clear that George Bush understands what you're doing, right?
Yes. So, are there any questions? And you can see the amp meter, it's pulling about 11 amps right now, which is based solely on the resistor that we have, or the mellow resistor.
Are there any questions in the meantime? Yes, Dr. True.
Okay, you communicated that the dash pod is set up in shape memory, and the spring is set up in super elastic.
Yes.
How did you set that up?
No, we're using two types. The settings is, there are two super elastics and two shape memory alloys.
Did you buy different alloys? Or did
Yes, we bought two different alloys.
Okay.
The super elastic, we're not interested on the phase transformation because this phase transformation occurs below normal temperature.
That was the next question I was going to ask. Where's the ACFF temperature for both of those? What's my finished temperature for those two alloys?
Yes, the finishing temperature for the shape memory alloy is 69, 68.
Okay, and what about the super elastic?
We didn't have interest on the super elastic because we are controlling the shape memory alloy. So we made the superelastics only for support. To support, because if we use only martensitic, which is shape memory alloy, it will damp and will stay down. It will stay up or down. We need a way to take some force up to take it back into shape. And the material will behave as in the curve that we have. It will transform with the help of the stored energy on the superelastic.
To slightly expand on that, as a segue, on a traditional shock strut damper, you have an actual coil spring and then you have a damper.
I understand.
Right, so what we're doing is we're using the austenitic or the superelastic as the actual spring mechanism, if you will, and for the martensitic as the replacement for the damper. And the inherent or the intrinsic material properties of the damping to make up for that when we have it in the fully elastic state, like as you see here. And as you can see now, that's kind of transforming back to martensite right now as it's cooling down.
Is there a reason why the spring component had to be nitinol?
Because we wanted to make it a fluidless system. And as far as our experiences have told us that that would be the best system that would give us some control over how much damping could occur.
The spring?
No, the spring.
The spring side?
Oh, the spring as far as, no, there
You'd cut
there
your
was no
costs
reason.
substantially if you had gone
Put a
with
spring
a
there.
No, I understand
simpler
what you're saying,
spring,
yeah.
because you're not getting any gain out of that, that's why.
This is true, that's true. That is a bit of an oversight. So we could have gone with the traditional stainless steel spring or whatever, SAE 920, something like that. We could have gone that route.
Okay, thank you.
Any other questions?
So one
Dr.
more quick
Basil
one.
still here?
Sure, I'll throw it. Are you applying the current during the damping process?
Yes.
Okay.
To change it.
Yes.
Because as it stands, without perturbing the system, without adding any extra energy into it, it is in its most, it'll damp the best right now. It's optimized because it's full martensitic.
Right.
But if we want to change it, in other words, if the load was changing or the conditions were worse and we need to somehow change the K value,
Right.
then we can inject the.
So technically, you could have a microcontroller on the side that
Yes,
measured some readings and would adjust
exactly.
this one. Gotcha. Okay. Yeah.
We had some feedback from a thermocouple to know
Yeah.
what is the phase.
Yeah.
Because according to the phase, it will change the stiffness too. So if
Absolutely.
we know the temperature, we have some feedback, we can stop the heat delivery. And we can have control over it.
So one other quick one. I know. Anyway, I know your simulations weren't meant to be one-to-one, right? But how did they compare for the fully, say, either fully austenitic or fully martensitic nitinol to, say, I know you guys did some experiments placing different. So how did your specific K value compare to the simulation value?
We did a system dynamics analysis, and what we did was based on the array of springs and setup as far as parallel series, we got an equivalent K value. And from that, we solved for the damping coefficient of the system, because we just perturbed the system, and it was a very easy, known calculation, second order, ordinary differential equation, et cetera, et cetera. So once we got that value, we inputted that into the simulation, and the times didn't match it exactly, because like I said, friction and everything else, but the behavior, the overall trend did match. And as far as it didn't match exactly one-to-one, but I would say about 30% difference as far as time it took, because that's what we're looking for, time to reach equilibrium.
Very good. Dr. Monroe? No questions? All right, thank you so much.